Good afternoon. So this is the third of the fall 20 BCT lectures. And before we begin, I got my usual housekeeping to do. So practitioners and any of the AIA CEUs, if you already made arrangements with Western Mass AIA and Lauren, you're in business. But if not, you'll find Lauren's email in the chat and you can contact her and make arrangements. Practitioners or students who are in need of USGBC, continuing ed, contact Kath McCusker for the self-reporting paperwork, and her email is also in the chat. During the presentation, if you have questions for their presenter, who I'll be introducing in a moment, please send them through private chat to Kath McCusker. We'll then read them during the Q&A. You'll also have an opportunity during the Q&A if you want to ask questions, but for those of you who are shy, the chat works pretty well. And finally, for all students who are attending this for credit, be certain to follow both the deliverable and the deadline requirements. All right, so today we are privileged to have as our presenter Ms. Heidi Jandris. She's the Technical Resource and Sustainability Manager at Jandris Block. So Jandris Block is the leading architectural concrete masonry producer in the Northeast. 25-acre facility. It's located right down the road in Gardner, Mass. It includes a 17,000 square foot grinding plant, 7 acres of covered product storage, and 2 cutting-edge concrete block manufacturing plant. As a third-generation member of her family's business, Ms. Jandris grew up immersed in all things concrete block. Worked as a welder at the plant before receiving her Bachelor's of Architecture from Pratt Institute. So currently, Ms. Jandris is pursuing a Master's of Sustainable Building Systems at Northeastern University. We will not hold that against her. And she's simultaneously fulfilling her role as the Technical Resource and Sustainability Manager at the Jandris plant. Ms. Jandris's blog, Hey Heidi, is a demonstration of her commitment, technical expertise, and involvement in the concrete block industry. So today's presentation will offer a view into the technology and methodology that's behind an industry leader's effort to reduce our built environment's very substantial contribution to climate change. So please give a virtual welcome to Ms. Jandris.
Hello, hi.
No,
should I share my screen now? Or I was gonna say a little bit about myself, but you did a much better job than I could have done.
Oh, well, you can certainly share your screen now. You're getting a lot of virtual hand claps here on our screen. So go ahead, Heidi, whenever you're ready.
All right. All right, do you have my screen?
Yep.
All right. So this presentation, it goes over quite a bit of things that we've done in the last couple of years to lower our CO2 emissions, and also kind of some inherent sustainability that concrete masonry offers. So I'm having an issue. Hear me still?
Yep.
Okay, so I'm having an issue. Oh, there we go. Okay. So sorry, I was having an issue with my slides. I have so many screens open, I'm losing track of what I'm pointing at. So for the agenda, we're going to do a quick overview of concrete masonry, some of the aesthetic and assembly performance options. I'm going to go into carbon sequestration, explain what it is and why it happens, and also the differences between dry cast and wet cast concrete, and how this affects carbon sequestration. Then I'm going to go through some greenhouse gases and climate change through the carbon cycle, and then climate change scenarios and projections. And then we go into solutions, geoengineering, adaptation, which includes resiliency and passive survivability, mitigation, lowering operational carbon by utilizing thermal mass. We've got durability and lifespan of structures, And then we get into the good stuff, lowering embodied carbon during CMU manufacturing by increasing the amount of CO2 that's sequestered, and also by lowering cement consumption. And then what's new with product category rules? The next version of concrete masonry product category rules is coming out, and we're going to be including CO2 sequestration in our EPDs that we can make with the PCR. So for an overview, there's two types of concrete masonry units. We have gray block, which is structural, it's durable, resilient, it's got really good thermal mass, and it's also used for firewalls. And we also have, our architectural CMU, which is very durable. It's structural. It can be structural or veneers. It's also very resilient. It has good thermal mass. It can be used for firewalls. And also, it's also very beautiful. It can be used for both structural and veneers. We use a lot of specialized aggregates from all over the Northeast. And we have multiple finishes and colors available to us. So for architectural masonry, we have our smooth integrally colored units. We have this is also another type of integrally colored unit. It's got kind of a blend brick look to it. We have architectural split face. In this project, we have banding of split face and also ground face. And then we have our ground face units. We also have polished CMU, and I keep thinking this is a new product, but I think we've been doing it for about almost 10 years now, where it's similar process to grinding, but it's a very, very hard resin that polishes the face of the concrete. There aren't any additional sealers on this or any kind of coatings. And then we have a weathered or a textured polished CMU, which is a similar process to polish, but it almost scoops out the concrete behind the aggregate and then shines up the aggregate. So it almost has like a leathery kind of feel to it. So then we have, for our wall types, we have a multi-wive cavity wall. And this is usually an 8-inch block backup. We have room for insulation and then some sort of veneer. It can be, in this case, it's a smooth face CMU, but it can be brick, it can be ground face or polished. And here we also have our pre-insulated single wide wall. So this is a single block unit. Usually it has a different type of shape. Like in this case here, we have one web and the insulation inside the unit so that it conforms to current energy codes. And then on the right, we have our anchored veneer, which is usually a steel backup. And in this case, we see a ground face veneer. We probably do I'd say about 60% of what we manufacture at our plant is for this kind of wall structure, being the anchored veneer. So carbon sequestration, why is it and why does it happen? So it's traditionally been called carbonation, which is well known within the industry. It's part of the reason that concrete gets hard. It's part of the reason that the concrete shrinks. So why does it happen? So I'm going to go a little bit into cement production. So when cement is being produced, CaCO3, which is limestone, is taken out of the quarry. It is heated up to about 2,000 degrees in this large rotary kiln. This heat causes a chemical reaction. And just for quick and easy numbers, approximately 45% of the CO2 release for cement reduction is due to the energy used to heat up this limestone. So when the limestone is heated up, it breaks apart chemically and CO2 is released. And what is left is, here we have our CaOH, which is also what was called clinker. This clinker is then ground up and powdered, and that is what and that is where our cement powder comes from. But when water and aggregate is combined with the cement, it produces concrete. So from the moment concrete's produced, it begins to reverse the chemical reaction that originally released the CO2, and it begins to sequester the CO2 from the environment. The sequestered CO2 is chemically combined permanently back into the matrix of the concrete as nanoparticles of limestone. This has historically been called carbonation, like I mentioned, and about 40 to 50 years ago, it was studied extensively due to corrosion issues with rebar in the concrete, because as it carbonates, its pH decreases. So corrosion protection requirements for masonry and concrete have been figured out for the most part and are part of the building code requirements that haven't changed for about 50 years. But studying and researching carbonation, AKA carbon sequestration for environmental reasons, is fairly new territory within the industry. So I'm going to go into now some of the similarities between dry and wet concrete, wet cast concrete. The raw materials are basically the same, but with different ratios. Dry cast, which is what concrete masonry, concrete block is, generally uses a different gradation of aggregates. It uses less water and much less cement than wet cast concrete, which is also what we would, wet cast would be the same as ready mix or poured in place concrete. So looking at them side by side, on the left we have wet cast, on the right we have dry cast. By looking at them, you wouldn't be able to tell which is poured in place and which is dry cast. And dry cast is what CMU is, it's what concrete pavers are, and also adhered veneers, the kind of the stone looking adhered veneers, a lot of those are dry cast as well. So on the left, we have a block machine. So this is our mixer. So all of our raw materials are put into the mixer with a very, very small amount of water. And this is, and then we have on our right, we have our poured in place mixer. So it all happens here, and then it just gets poured right into the ground. And that's kind of the end of it. Where dry cast, here I have a video of our block plant. And so dry cast is also zero slump. So there's very little water in it. So this, from the mixer, the concrete gets poured down into the machine, and then actually vibrating. So once the block comes out, if I were to grab this, that's why we call it zero slump. So the difference here is that a slump concrete is has got a lot of water content in it, and that water content is very important for the strength also. So here's a little video of a slump concrete.
We'll invert the cone, measure down to the offset center, and get your reading for your slump.
Yeah, so because of this difference in slump and therefore water content, dry cast concrete has a unique structure that helps to facilitate accelerated CO2 sequestration when it's compared to poured in place concrete, which we're going to get to in a little bit. So another one of the main differences between dry cast and wet cast is that we use a kiln. And the kiln isn't all that hot. It's probably only about 140 degrees around, depending on the mix. But essentially, the reason for using this is to cure the concrete, like give it a jump start, starting the hydration process. And that's another way that we gain our strength. The first way with the vibration and compaction of the machine. That's one way we gain our strength, and also the curing. And so dry cast is not completely dependent on cement content to gain our strengths. There's other parts of the manufacturing process. So this is so due to the CMU being dry cast, it has a more porous structure when compared to wet cast. On the left, we have a zoomed in image of dry cast, which shows the interconnected void structure of the concrete. So this allows some air to penetrate into the CMU. which enhances the ability of the block to sequester CO2 over time throughout the entire block. Not all CMU have this structure. Some are more dense, some are less dense. But comparing this to the image on the right, which is a wet cast concrete with air entrainment. So even though it does have the air in it, it's not connected. The air pockets are closed off from one another. So this is why poured concrete sequesters primarily at the few outer millimeters, which are exposed to the atmosphere. So because of this structure of concrete block, there are, this ASTM C90 has absorption limits. So if the block conforms to C90 and it's properly flashed, weeped, and it has crack control that's detailed properly, moisture won't be an issue with concrete masonry construction. So for exterior applications, because of this, we always put in integral water repellent in the block. This is a very quick water droplet test. On the right is a block with integral water repellent. And if you put, this is like a five milliliters of water, you put it on top, it just sits right on the top. I think that I let this test go for, I think it was 4 hours before I left it. But on the left here is a block with no integral water repellent, and you put that water right on top and it just like sucked it right up. So it really just shows the difference between block with integral water repellent and without. Another test for water repellency is our ASTM E514, which is a spray bar test. The block on the right had no integral water repellent, and on the left it did, and it also had it in the mortar. So you can see that after over time, water starts seeping in if it doesn't have the integral water repellent. So back to the void structure. Because of the more porous structure of dry cast, it does, so we have to control water penetration with CMU construction, but all that surface area and void structure, it produces kind of like a carbon dioxide sponge. So these images are of a fatal phenylene indicator solution test. So this is one of our blocks that got split open on the left. And if this indicator turns purple, the pH is above 8.6. Where the solution remains colorless, the pH of the concrete is below 8.6, suggesting carbonation. A fully carbonated paste has a pH of about 8.4. The block on the left is our dry cast. On the right is some wet cast concrete. The rate of carbonation in wet cast is slow, averaging carbonation rate of about 4 millimeters per year, and it slows down with age. The wet cast on the right is somewhere around 6 years old, and carbonation is shown only at the outer crust of the concrete. Until recently, the concrete masonry industry assumed that the CMU would carbonate the same way. However, recent testing we've done has shown otherwise. The block on the left is about 2 months old. And as you can see, the carbonation is occurring into the concrete and not just at the surface, and at a much more rapid pace. So I had a lab perform these tests on 3 different CMU. Sample A is 6 weeks old. Sample B and C are 20 plus years old. Sample B was in our yard, exposed to the environment. I wanted to see if water content would affect sequestration rates. And the one on the right was stored inside for all this time. I think it was part of a shelving unit above the block plant for a very long time. Probably much more than 20 years. So the older block is fully carbonated. So a little bit about the testing. While there are proprietary carbonation tests, our industry is looking and developing an industry-wide test method. One of the current test methods under development is a thermal gravimetrical analysis, or TGA testing. And what this testing does is concrete is ground up to be extremely fine, and it's heated. And different substances are burned at different temperatures. And the weight of this powdered concrete is continually measured. So carbon burns off at about 550 to 900 degrees Celsius. And the ground concrete is weighed before and after this temperature range. And from there, we can tell how much carbon left the test powder. So the carbon content of the raw material is compared then with the carbon content of the manufactured block. And this determines the amount of carbon that was sequestered during the manufacturing process and at different ages of the concrete. So this test method is currently being looked at by the industry for viability to measure the amount of carbon sequestration that occurs. So what I had preliminary TGA testing done on these samples, and this testing tells us that sample A had a sequestration rate of about 13 to 17%, and that 13 to 17% is percentage of the total amount of CO2 given off during cement production for the cement that was used to make this block. The 20-plus-year-old concrete, which is fully carbonated, showed TGA testing of about 25 to 28%. And just a little note here, and I am going to get into this a little more. Roughly, the potential to carbonate is around 45%, and that's due to the amount of CO2 emitted during the chemical reaction breaking apart the limestone. All right, so here is another phenolphthalein test at 6 weeks on the left, and then at 4 months. So you can see that it's starting to go further and deeper in and carbonate more within 4 months. I have this same test, the same block, sample A, and it's slated to be tested again, I think next week. So that would put it at about 8 months, I believe. So I'm really interested to see how much and how long it takes to fully carbonate. So the sequestration potential, about 40, and these are very, very rough numbers. About 45% of CO2 emissions is due to the heating, 45% due to chemical reaction, and 10% to other processes, of manufacturing. So the CO2 emissions due to heating and other processing can be improved with increased efficiencies. For example, Heidelberg Cement Company, in their 2019 sustainability report, they reported a reduction in CO2 emissions by 22% since 1990, and they have a goal of 30%, so that's substantial. So increased efficiency, excuse me, of the cement plants will help to shrink the CO2 emissions given off by the energy that it takes to make the cement. But the CO2 released due to the chemically breaking apart of limestone won't be affected by these efficiencies. But we can potentially get a good portion of this back through sequestration and using technologies to increase sequestration rates. So of our sample, sample A at 6 weeks, you can see here that we've got 13 to 17% sequestered CO2. So that takes up a good amount of this potential. Here we have this 20-plus-year-old block, and it was 25 to 28% sequestered CO2, which uses up another huge chunk of the potential. So what about the remaining? How about that? This is another current area of study and research that we've been working on at our plant, how to get the most sequestration possible by changing the way we manufacture and our raw materials. And our first testing is at 28 days, but we're also looking at beyond the 28 days. So I'm going to talk a little bit about kind of some of the manufacturing process that allow for improvement, but that'll be more towards the further on. But I will say that we have been researching technologies to increase the amount of CO2 sequestration at 28 days. So why 28 days? Well, first of all, this would consider to be cradle to gate for our EPDs, which are currently cradle to gate. And it's also when we no longer have control over what happens with the CMU. Is it covered with non-breathable paint? Like, we don't know. Covered with insulation? Probably. put in the ground? Very good possibility. We just don't know. So we can't really, so as a manufacturer, kind of in the beginning of this research, we kind of can't really worry at this point too much more about more than 28 days. Even though we know it continues to sequester if it's in the right conditions. So one of the technologies we've been working on increases the reactivity of the cement we use. So this not only lowers the amount of cement we need to use, which is huge for global warming potential, which I'll show you a little bit when I show you our EPD results. And also because it's more reactive, it increases the sequestration of ambient CO2. Another technology we've been using injects CO2 in the mixer during production to increase the rates. And I'll get into this a little bit deeper further on in the presentation. So I'm going to get into greenhouse gases and climate change, starting with the carbon cycle. So the largest reservoir of carbon in gigatons on Earth lies in its sediment, and this includes fossil fuels and rocks, not in its atmosphere, in vegetation, or in the ocean. Over intervals of millions of years, slow exchanges among the rock surface and reservoirs can cause large changes in atmospheric CO2 levels. So we kind of have our very slow carbon cycle in the atmosphere down into the ocean, goes into the rocks. And we also have our shorter carbon cycles from vegetation into the soil and into the atmosphere. So the input of CO2 into the atmosphere naturally is through volcanoes. So the rock in the earth gets heated up and it spews out of volcanoes and it blows CO2 up into the air. So it releases all those gases, also hot springs such as Yellowstone National Park. And to make this happen, it requires high heat, which should sound familiar during, as I explained, this how cement's produced and releases CO2 with high heat. So the chemical weathering of silica-rich rocks on the continents removes CO2 from the atmosphere. It's dissolved into the carbonate below the ground and gets stored underneath the ground. I think those, I remember visiting a cave and seeing those stalactite and stalagmites. So that's one of the ways. So also ions are dissolved in river water and transported from the river and into the oceans. From there, little animals make their shells using the calcium carbonate, and it sequesters the CO2 out of the atmosphere. These animals eventually die and go to the bottom of the ocean. And then when the plates cover over themselves, they bring it back into the earth, and then it goes up in volcanoes. And that's the larger carbon cycle. So this is all part of feedback loops that have regulated climate on the Earth for billions of years. At the onset of a warming trend, increased temperatures and precipitation increase chemical weathering, which increases the CO2 removal from the environment. So increased precipitation naturally removes the CO2 due to this chemical weathering. In the same way, when the colder climate, decreased temperature, decreased precipitation, decreases that chemical weathering, it stops removing CO2 and it reduces the initial cooling. So it's all part of this amazing Earth that we have and this living system that regulates itself. So left alone, the Earth would absolutely regulate itself. But the problem is, pretty frankly, is us. We have been pumping out CO2 faster than the Earth can regulate or even can pump out on its own. So this here is these data points initially published in the Nature Research Journal in 1999 were collected over Antarctica ice cores, and the ice cores then reconstructs the temperature and greenhouse gas correlations over the last 425,000 years. So correlations between temperature anomalies and atmospheric CO2 show that the temperatures slowly rise as the CO2 levels in the atmosphere rise. So these CO2 levels are in blue and the temperature are in the gray. As CO2 levels sharply fall, the temperature also sharply falls. These peaks and valleys in the data represent the cyclical nature of interglacial periods, which are caused by the Earth's pretty much by the cyclical and orbital changes. So these follow orbital changes in our solar system. So while this correlation is well documented, temperature changes and climate variability are caused not only by CO2 concentrations. There's several other natural forcings such as solar activity, volcanic activity, dust, vapor in the atmosphere. This vapor acts as a greenhouse gas, which also affects global temperatures. But the key word here is natural. So the difference now in the last 100 years or so, we are spewing out more CO2 into the environment at a quicker rate than any natural forcing could do. Since the Industrial Revolution, our CO2 levels and temperatures are rising much faster than they did during the last extreme greenhouse climate, which was called the PETM, standing for Paleocene Eocene Thermal Maximum, which was roughly about 55 million years ago and lasted for about 100,000 years. This interval was characterized by the highest global temperatures from the Cenozoic era until present. It took thousands of years for the temperatures to rise this much. And like I said, our current CO2 levels are rising much faster than they did leading up to the PETM. So we aren't at the levels of the atmospheric CO2 yet that were at the PETM, but we're headed there very quickly. At the beginning of PETM, the Earth was already relatively warm, much warmer than it is now, so we got to give it that. There were no polar ice caps at the start of the PETM. But temperatures rose from 5 degrees to 8 degrees Celsius, making the temperatures at the poles 74 degrees Fahrenheit. And the ocean waters were 68 degrees Fahrenheit. This was an extreme warming, which occurred after an extreme release of carbon dioxide and methane and other greenhouse gases. One hypothesis for where these gases came from is that there could have been a rash of wildfires. Another is that there could have been giant seams of coal exposed to volcanoes. Or it could even been that there was mild warming causing methane to be released from tundra. We may never know. There's all kinds of hypotheses out on that. But one thing that we do know is that during this PTM, there's fossil evidence that's been found in the Arctic Circle for ferns, ginkgos, and redwoods, or in the Arctic Circle. And also fossils can be found of alligators, crocodiles, and turtles as far north as the polar forests of northern Canada. During this time, the globe had warmed more than humans had seen it up until that point. And it shows how extreme effects of climate change can be. And it allows for some pretty striking comparisons. So going into projections. The IPCC, the Intergovernmental Panel on Climate Change, developed a series of scenarios for greenhouse gas emissions. In dark blue, we have the actual CO2 emissions, which is a jumping off point for all 4 scenarios, which are called RCPs, standing for Representative Concentration Pathways. RCP 8.5 is in pink, which is a scenario with very high emissions. 6.0 is also very high, but not as high as the 8.5. This 4.5 in blue is intermediate greenhouse gas mitigation scenarios. And 2.6 is very stringent mitigation. This is what could happen if we really got it together quick. So scenarios without any additional effort to constrain current emissions leads to pathways somewhere in between these two. We're going to look at a climate model which takes data from scenario 4.5, which is an intermediate to fairly drastic lowering of CO2 emissions. And I'm going to look at a period from 2000 to 2100. So this climate model looks at 2 periods, 2 20-year spans. One of them is 2000 to 2020, and the other is 2080 to 2100. So around the equator, the changes are relatively small, but much larger at the poles. And you can see that around here, it's probably a difference of 3 degrees. Down at the poles, we're up to about 6 or 7 degrees change, which is huge. So the reason that it changes more around the poles is that the polar ice caps start to melt, and due to the albedo effect, less solar energy is reflected and more solar energy is absorbed, and this creates a feedback loop. Increasing temperatures more in areas than where the albedo remains unchanged. Is this enough to bring alligators back to the Arctic? Probably not, but you can see where this is headed if we don't get it together. So global emissions by sector. Building materials and construction accounts for 11% of CO2 emissions, and this is according to Architecture 2030. And so now I'm going to go into solutions. And so these solutions are geoengineering, adaptation, mitigation. And so an integrated approach is needed. Comprehensive risk management includes a family of solutions drawn from all 4 of these approaches. And this was published in Physics Today back in 2014. So we need to have mitigation, which is reducing emissions, geoengineering, so introducing changes to counteract emissions, adaptation, which includes plan for impacts, build resiliency, and improve response capacity. And then we have our knowledge-based expansion, which is scientific assessments and technological developments. So first I'm going to talk about geoengineering, and not because I think it's the most important. I just wanted to get it out there, and doing it first flows with the presentation better than bringing it in at the end. So there are many different geoengineering solutions out there, but they vary in effectiveness, cost, and risk. Sorry, I have a jumpy fingers. What's going on? Sorry, let's go back. Wow, that really got jumpy. All right, found it. Apologize for that. My mouse pad migrated over to my keyboard and had a little mischief going on. So geoengineering solutions that do not negatively affect the Earth system as a whole are required to keep the Earth from entering this greenhouse climate. Several solutions would be needed, but they need to work economically and ecologically. There's several proposals out there, but not all of them make sense. Excuse me. Mirrors in space are way too costly, and they have very questionable efficacy. So yeah, it would be like hanging mirrors in the sky reflecting solar radiation. Maybe we could hang them on the clouds, perhaps. I don't know. So then there's also the adding sulfate aerosols to the atmosphere, which would reflect solar radiation. One of the downsides, it doesn't last very long, and we have no idea what creating clouds over the oceans is going to do to climate and weather patterns. Another proposal is to add iron fertilizer to encourage marine life in the current dead zones where there's a lack of oxygen. I mean, we have no idea what this would do and what the repercussions of doing this would be. Of all the strategies, carbon capture holds the most promise, I think, along with afforestation, which is reintroducing forests and leaving them there so that carbon can be stored in the trees and the soil beneath. As trees are cut down, not only are the animal habitats destroyed, but the trees stop taking in CO2 and they release the CO2 stored in the surrounding ground. So different types of trees hold different amount of carbon in the soil. On this image from the USDA website, trees from tropical forests are estimated to hold much more than 50% of their carbon in the actual trees, and the rest is in the soil. Trees from the boreal forest up in Canada, they hold as little as 5%. in the actual tree, and the rest is locked up in the soil. The wetlands, and the peatlands. Absent of human intervention, it will largely remain there. So then we get to carbon capture. It seems to have the most promise. Not only can it create a carbon neutral fuel for transportation industry, it could also capture CO2 out of the atmosphere and solidify it for storage. The Wall Street Journal reported on February 12th in 2020 that Exxon, Mobil, Chevron, and Microsoft and other big corporations are focused on reducing the cost and energy required to capture carbon dioxide. Hopefully with this group of large corporations working together on this, it'll soon become common practice. So adaptation, plan for impact and build resiliency. In most parts of the country, there's natural disasters. So this was after Superstorm Sandy in 2012. This was an interview I heard on NPR, and I looked it up from 2012. The only thing we can do, insurers say, is build our buildings safer and better prepare for what will eventually come. So concrete masonry structures are safer structures. They're very resilient to floods and hurricanes, to fire, high wind events, and mass walls provide passive thermal performance. It's considered to be a Class 5 building material by FEMA. It's highly resistant to flood and water damage, including the damage by moving water. These materials can be successfully cleaned and rendered free of harmful pollutants. The IBC requires the use of flood damage resistant materials in area prone to flooding. This is an image from Hurricane Katrina. After Katrina, this was in Mississippi, and the only structure remaining in this area is a concrete structure. This is Superstorm Sandy again, 2012. This is actually from my old neighborhood in Red Hook. I used to live in Red Hook, Brooklyn, and this whole area flooded. And because these are masonry structures and very resilient, this is a Google Earth image from 2018. So this community could rebuild and thrive, and businesses didn't have to leave. Another thing, resistance to fire, it's non-combustible, it remains structural under fire conditions. So there's two types of systems. There's passive systems, which is non-combustible and compartmentalization. And then active systems would be what sprinklers are. So this is an interesting video, and if you, it's on YouTube. If you Google legacy room, modern room, and UL laboratories, you can watch this video. I'm going to go through it pretty quick, but something that's pretty sobering is in recent history, fire codes have become more and more dependent on active systems being sprinklers, allowing for more structures to be made of combustible materials. At the same time, fuel loads in our living room have increased by about 10%. This legacy room on the left is from about 100 years ago. The furnishings are wool, horsehair, cotton, very traditional. Modern is plastic furniture, pleather, foam padding, very little natural materials. So this makes for a very combustible room. Plastic is a derivative of oil, which is a fuel. And plastics give off a vapor, which is combustible at high temperatures during off-gassing. So let's start this going, and I am going to fast forward it for points, for the important points. So synthetic materials today have about 3 times the BTUs compared to traditional materials. And houses also have about 3 times the amount of stuff inside that they used to. This means about 10 times the fuel in modern homes versus traditional homes or legacy homes. Just one recliner has enough to flash a room. So these firefighters are starting the fires in both of these rooms. So at about 1 minute is probably by the time you notice the fire and you call the fire department. 911 gets dispatched somewhere, if they're very efficient, about 2 minutes. So this is where our fire's at. So at this point, the legacy room has a small controllable fire. On the right, there's a lot more flames. And it's just waiting for the right mix of air to ignite it. And then we're gonna go to 3 minutes. So here we are almost at flashpoint. The fire department hasn't even gotten, you know, they haven't even left yet. So here at 3.5 minutes, I think we get to flashpoint, and it's due to like all of these gases you see is flammable vapor from the furnishings in the home. So the modern room flashes about 3.5 minutes, and the legacy room flashes at 29 minutes if we were to continue on with this video. So fire resistance and non-combustibility is a big part of resiliency. So now I'm going to go on to passive survivability. Here is a graph showing in green mass walls and the interior temperature of a mass wall structure versus the interior temperature of a light frame structure. And in blue, we have the exterior temperature. So you can see that with mass walls, they really kind of hold the temperature, where a light frame structure just very much stays the same as what's going on the outside. So, I mean, following a natural disaster, it might be days or weeks before power is restored. And mass walls can really help to help with the passive survivability of a structure. Another example of passive thermal performance. This is Marsha's garage. That's my sister. She's got a masonry garage. And in the summer, when it got really hot, we going into this garage, like it felt about 20 degrees cooler. So you can really feel that thermal mass. Believe it or not, I grew up in a 100%, almost 100% block house. Block stairs, block floors, block walls, everything. And we needed no air conditioning in the summer just because of all that thermal mass really held the temperature. I think my father got the blocks cheap or something. But, so a couple other strategies. This is from the 2030 palette. We have direct gain heat storage, where the wall is designed to absorb solar radiation during the day, like up here, and then it releases it at night. This is a thermal storage wall where this is designed to absorb the solar radiation from the windows and then emit it to the inside of the structure on the other side. Mitigation, reducing emissions by utilizing thermal mass. So mass walls in southern climates absorb and store daytime solar heat for release at night when it's cold. But then in New England, you know, like where we have cold climates, we can utilize that thermal mass on the inside of the insulation, and it absorbs and stores the interior temperatures of the conditioned spacing, which minimizes thermal lag. Which is thermal lag is that chart that I showed you where the thermal mass kind of keeps a steady temperature. So kind of looking at a real world kind of code-based way to evaluate thermal mass. This is a table out of ASHRAE, which informs the International Energy Code. And for climate zone 5, which is what we are here in Massachusetts, a metal framed building requires a U factor of 0.064. A mass wall requires a 0.09. So the ASHRAE in the Energy Code takes into account thermal mass when giving you the requirements to pass code. So looking at assembly number 1 is a metal stud with 2 inches of insulation. On the right, we have a CMU backup with 2 inches of insulation, right? So they both have the exact same amount of insulation. This metal frame with that 2 inches in climate zone 5 fails code by 14%, where same amount of insulation with a mass wall behind it exceeds the code by 36%. So it provides a much more energy efficient envelope with the same amount of insulation, which allows you to actually use less insulation to pass the code. Yeah, so I am pursuing my Master's of Sustainable Building Systems at Northeastern, and I'm currently in a life cycle analysis course. And my overall project is going to be to compare wall assemblies and take these things into account, you know, like using less insulation, like utilizing the thermal mass, also taking in the sequestration of the block. So that's my big big project, and I can't wait to get into it. I'll let y'all know what I find out. So durability and lifespan of structures. So mitigation. So this is mitigation. So we're reducing emissions by building durable structures. So these are some Sears homes built in the early 1900s. They were built using one of these little hand machines, right? This is how my family business got its start, was making block with these little machines by Sears. I actually found one of those over the block machine. And once you start seeing these house types, you start seeing them everywhere. It's kind of like being in a field and seeing one spider. You start seeing them everywhere. But these structures are well over 100 years old, and they're standing up extremely well, most of them. And I'm going to finish this little section here with a common misperception. I heard this once at a talk, and it had nothing to do with architecture, but it was just it was something about looking at the way you perceive things, and your perceptions are not always true. And it was the common misperception was medieval castles were built of masonry. Like, everybody thinks that these castles are masonry, and masonry lasts forever. But in reality, most of these medieval castles were made out of wood, and they just aren't around anymore. They did not stand the test of time. So now I'm going to get into lowering embodied carbon during CMU manufacturing by increasing CO2 sequestration and lowering cement consumption. So now we get into mitigation and knowledge-based expansion. So I'm going to get into this technology. So like I said, it's a technology that we've been looking into, and it helps us to lower consumption and increase sequestration, and it doesn't affect the strength of our units. So this heightened cement paste reactivity. So what we do is we change the way we manufacture. We make the cement paste more reactive. So that is why we can use less of it, but it also increases the amount of CO2 sequestration, because that cement's actually more reactive. It essentially creates a carbon sink out of the block. So zooming into this is a very dense CMU. We can see the void structure that we looked at on that previous image of the microscopic block. And in blue, we see the void structures that we saw in the last image. But something that we see here is that in red is all of this unhydrated cement. Now, this is kind of like the way that we traditionally make block. We end up with a lot of this unhydrated cement. So it's pretty much wasted cement in there. And these clusters of unhydrated cement form a hard shield around them so that carbon dioxide will never get to them. So one of the things that this technology does, and the main reason that it works, is that it liberates these little clusters during manufacturing, and it leaves them available to carbonate. So this allows us to utilize that unhydrated cement. And this is one of the things that can bring us back to that 45% potential, which was kind of like the top amount that we could potentially sequester. And also, because of this, less cement can be used. So these are two identical photos of CMU. One has reduced carbon and the other one is standard, and same strength, same performance. One has 42% less global warming potential. So looking at our EPDs, we had environmental product declarations done for every single one of our mix designs. That was about 400 of them, and it was really interesting, some of the things we got from it, like using crushed concrete as an aggregate. We thought we were doing the right thing by having post-consumer recycled content, but actually we found that it brought our global warming potential up, and mostly because of the quality of the aggregate. We had to use more cement. And we weren't saving it from the landfill. It was it's used as road base, so little things like that we didn't think of. And they, so it also showed us a lot of, some of our raw materials are much more energy intensive than we would have thought. So it really showed us a lot about our raw material choices. So here I have phase one of what we've done with this technology is lower our cement by 10%, right? And so I have a simulated industry average here. And the reason I'm calling it simulated is because it uses our plant data with an industry average mixed design, because I don't have, our industry did not do an industry average. So I kind of made my own, and I did it just for myself. I was interested in it, but so it's not a true industry average, but it kind of gives us a starting point. And here is what our global warming potential is from our normal weight CMU. And then reducing our cement reduction, it brings this down to 261. Next phase is 10% reduction with 8% sequestration. And then what we're currently working on, and we're not quite there yet, but hopefully we'll be soon with this technology, is 15% cement reduction with 12% sequestration. And this is at 28 days. So I just want to talk a little bit about these global warming potential numbers. These here are from third-party verified EPDs. And our industry, and I mentioned it's simulated because we don't have a current industry average. And I did the best I could for comparison's sake. These here, I calculated the global warming potential based as using our EPD as a starting point, and then the percentage of sequestration that we got. So these were calculated and are not from EPDs. But this brings me to the last part of the presentation, which is really exciting. I've been on the committee developing the PCR for concrete masonry was up a couple of months ago, and I've been working along with National Concrete Masonry Association to develop our next PCR, which is product category rules, which is how we conduct our life cycle analysis to get our EPDs. And we will be showing CO2 sequestration in our EPDs. Well, we'll be able to if we have if we have testing. So we will be able to get that credit for sequestration shown in our EPDs, which is really exciting. Because it's something we've always known that happens, but we just had no way to measure. So it'll be reflected in the global warming potential impact indicator, and it's going to be 28 days, and it'll be from cradle to gate. And accounting for the reaction of atmospheric carbon dioxide, and it's going to be manufactured with manufactured concrete products, which is going to include pavers, it's going to be adhered veneers, and it's going to follow the ISO standard 21930. So what's next? Utilizing methods for CO2 injection to increase sequestration rates, utilizing technology to increase cement reactivity, which increases sequestration and lowers our cement consumption, and also improvements to our manufacturing process. We've done a lot in the last 12 to 15 years. We recycle the heat given off by the hydration in our kilns. We're able to recycle that to heat the kilns. And by putting that system in, we're able to lower our fuel emissions to heat the kilns by about 50%. That was done about 12 years ago. We have solar panels. We get about, on average, 80% of the electricity required to run a block machine with the solar panels. We have many other things that we've been working on, but that's my presentation, and we can open it up for Q&A.
Thank you, Heidi. Maybe it'd be the thing to do would be to stop the screen share now too.
Okay. All right.
So terrific. And Kath, do we have some questions for Heidi?
Yes, of course we do. Thank you, Heidi. All right, first question. You mentioned breathable paints. So exterior CMU often need to be waterproofed. How does that affect CO2 absorption?
So there's a couple types of paints. I think that, first of all, if a CMU wall has integral water repellent in it and it has weep holes so that if water does get in, it can escape, you really do not need to have a sealer, especially with like a cavity wall construction where you've got the weep holes and the flashing, right? But the only time I would recommend a sealer would be for a single wide wall, like where we have the insulated block, kind of using everything you can, kind of belt and suspenders kind of approach. We would recommend a sealer then. And in that case, we would recommend a breathable sealer. It's like a silicone, and it doesn't allow water to get in, but it allows it to breathe. So if you were in a situation though, where you know, like a car wash where you have a, you know, very impermeable coating, then it would impede sequestration. You know, but as long as it's breathable, and you wouldn't want to put a coating on the outside of a CMU wall that was not breathable, because then you get that, you know, the bubbling of the paint and that kind of thing. So it's got to be a breathable sealer if you are to use it.
Right. Okay. Next, what about the impact of fire, water, and resulting toxic chemicals on rebar in concrete, especially for a porous material like CMU?
So that whole carbonation issue as a deleterious to rebar, that's with poured concrete, and we saw those images where this carbonation only happens into, like, you know, 1/4 of an inch or so, right? So if you know, if the mix is right, it does not actually get in to reach the rebar. So the difference between the poured in place concrete and concrete block, right? So we have the cores, right? And so the rebar is in the cores and it's surrounded by grout. It doesn't actually touch the carbonated block. So the carbonated block it doesn't have steel in it, you know, so that's kind of, it's almost like a, what's the word? Simpatico? I don't know. Like, you know, like it sort of works in our favor. So we have the more porous structure, but we also aren't relying on that for corrosion control of the CMU because it's in the cores, like it doesn't touch it.
Right.
Did I answer that one right?
Yeah.
Yeah, okay.
Yeah. Next, I'm going to introduce Peggy Clouston. She's a faculty member here at BCT, and she has an interesting counterpoint to your comments about afforestation and carbon sequestration of keeping trees in the ground, like the carbon that trees and their root systems will sequester. So a counterpoint to that. Peggy, take it away. We can't hear you.
Peggy, you got to unmute.
You have to unmute.
Oh no. Oh, we can't hear her.
Peggy, you keep talking, but no one hears you.
Oh, technical issues. Well, the image behind her is of the beautiful design building that we work in. So I'll read Peggy's comment, and in the hopes that she can get her technology working so that she can contribute to the conversation. But just a counter comment about preserving forests.
Mhm.
Many studies show that if forests are harvested sustainably and used in products like mass timber, more carbon can be sequestered than if the forests are left alone over time. Our UMass Oliver design building is a great example of how to use forests to create award-winning carbon neutral buildings.
Yeah, so I mean, that is I am very well aware of that point.
Did I just hear you, Peggy?
I can't seem to get it to work.
You're
Can you
good.
guys hear me?
Yeah, you're
Yes.
good.
Oh, sweet. Okay. Well, so I missed kind of what's just happening. Actually, Heidi, first of all, I want to say great presentation. That was very interesting, and I commend you on your work. We need more people like you who are really trying to make a difference with the building materials that go into buildings. So that's really an important thing. And I'm looking forward to seeing the work that you do with your thesis and the EBDs that come out on the buildings that you've identified. But I did want to make that counterpoint that Kath just talked about, because our Olver design building, it's up to 13 awards now for its sustainability. And the IPCC is recognizing that if we use our forests as working forests and sustainably harvest trees, we can make a huge difference building with wood and sequestering carbon in our structures, just like this beautiful structure right behind me, the Olver design building.
Mm-hmm.
So did you want to say?
I do. And yes, I understand that point. I think that, and I didn't want, and I knew I was presenting to I knew who I was presenting to, so I didn't want to go too deeply into this topic, but if it's sustainably forested, it is. And I think what's interesting, if you go on the IFCC, what is it? Is it the IFCC certified? What's the certification? The certification for wood.
It's FCC.
FCC, okay. So, I mean, if you go onto their website and it talks about, you know, sustainably forested wood, most of the wood that we get is from Canada, and it actually says it right on there that not all of their wood that's certified is sustainably forested, and they do allow clear cutting in Canada. You know,
that's
yeah.
true. SFI and FSC, that's all very important. Most of the mass timber that's being produced today is using certified wood. That is a major component, and not anyone in the wood industry will argue with you there. The pollution that is spewed into the air from the manufacture of concrete, not necessarily CMUs, this is not my area of expertise, and steel is really doing great harm to the environment. So we need to start looking at how we can manufacture products that base from renewable structures or renewable materials like trees, like plants, like bamboo, like high fiber modulus materials. So yes, certification is an important aspect to it, but it's the EBD that you identified, the full life cycle assessment, that's really critical here. So we got to look at eutrophication, acidification, everything right across the board and put numbers to it.
Yeah, I mean, I agree. I think too that, and yes, I don't dislike wood. I actually like wood quite a bit. But there are other factors. See, I guess I think one thing that I wish would happen is EPDs that go beyond gate, right? Because durability and resiliency should be a part of the story.
You bet.
So I think that, you know, with CMU or concrete in general, like that is a huge part that like we've got the impacts right in the beginning. I'm not going to deny that. That's why I'm doing my work, right?
Of
but
course.
when you look at the overall lifespan, you know, it's not being compared equally. You know, so I think that will happen over time. I mean, I think this whole looking at environmental impacts with EPDs is very new.
You bet.
You know, so
That's right.
You know, so hopefully we'll have a better picture of it, because just looking at cradle to gate, which is what we're doing now, is very it's only part of the picture, and it doesn't take into account everything. I mean, you know.
Right.
Yeah,
so
yeah.
We agree.
Yeah.
Well, I think that's true, that you both agree, and that it's going to be defeating this climate change is going to be coming at it from all the different directions. So one thing that I'm especially curious about is that you spoke about, it was 14 or 18 years ago that you started reducing energy loads at Jandris Block. So I'm just guessing, but I don't think that was you orchestrating that. So what was it? That moves us back until around, that's the early part of the 21st century. So the generation before you was who started this instigation, and that was who inspired you to move in this direction?
No.
Oh, okay.
Well, I mean, that's actually my brother. My brother is a little bit older than me, and he's been running the show since about 2000. But he did these things to save money, you know? So, I mean, that's actually another big factor in all of this, is money, right? So I did a ton of research, you know, for different types of recycled content things, and, you know, but if it costs a little more money, it never took off. But so I guess I digress, but I think the saving money and being more efficient. So I guess more efficient manufacturing it saves money, but it also lessens our impact on the environment because we're using less resources. So a lot of these things so my brother runs production. Like I've gotten him to kind of come along with me because it gets to save him money, and I get, you know, and I get to see the environmental impact. So I think it's been really interesting because we're a small enough company that we can actually move the needle. Did I answer that question, or did I get sidetracked?
Oh, it's good. Well, it's important. I think it's important to know how it comes along that someone who's not all that much older than many of our students are having a substantial impact on a substantial industry that's part of our built environment. So I was curious to see how that came about. And I'll just do one more question before we run out of time, and then we get back to Kath, is that how much of the rest, so there you are in the Northeast as a leading manufacturer. How about as you move into this niche of better performing CMUs from whether it's an energy perspective or carbon sequestration, is that going to improve your market and with what might be going on in the rest of the country, which if I saw where that graph was of the industry average was considerably higher.
Mm-hmm. Yeah, I mean, that's sometimes I feel like with this stuff, when I go to the the meetings, the national meetings, it's kind of like Heidi in Canada are really pushing this stuff,
Yeah.
but I think I do think this is a lot of this is starting in the Northeast as well, so it's very important, and not all the Northeast, like it's really kind of Massachusetts is one of the hot spots for sustainability, as far as I can see, and also the West Coast. So it's we have a producer that is doing the same kind of technology as us on the West Coast, and they're doing the same thing. So eventually it's got to move in, and I think that with designers specifying things like EPDs, and sticking with it, it's one thing to put it in a specification, but to actually make sure you get it, is important, because then manufacturers can't ignore it. So it's things like that. But it's I do feel like I am pushing the
Well, that's why you're
the
here.
rest along.
So, Kath, any more questions in there?
Yeah. So what percentage of CO2 emissions come from global concrete production?
Oh, global versus United States. That is a really tricky question, and I'm just starting to learn more about that. There's so much to that. I know that the global numbers, we are in our PCR that we're working on right now. We're not allowing North American EPDs to use the global numbers, because there's so many things put into that average, right? Like they use a lot of slag over there, because we used to in the US use slag, which is a byproduct of the steel industry. Steel industry has left. Slag comes from overseas. It's now expensive, so we don't use it as much, right? Like there's so many factors to it. But your question was, what's the difference? And I'm not sure about that. I don't know what the difference is. I just know that in the European averages, and that's the only one I really know about, they use other factors into their average that we don't use in the US.
Right.
So that one's tricky, and I'm working through that one.
Okay. And you and Peggy touched on this, but I'll ask this question, as it's perhaps a better point to go out on. How important is the life cycle analysis for understanding sustainability in the built environment?
Huge. Yeah, I mean, looking at our EPDs, like something like in the Northeast, we use a manufactured lightweight, like that affects our global warming potential a lot, where it doesn't in other parts of the country. Like that example I gave you of using recycled content, it brought our global warming potential up. Like we never would have known this. So yeah, I mean, I think that is huge. And I also think that what I'm hoping to get more into the life cycle analysis, because I think my industry, from what I'm learning from the class I'm taking, my industry has not been very great at supplying these databases with numbers, and I'm hoping to contribute to that.
Yeah, well, I mean, I would second that. In BCT, we have been advocating to get a life cycle, a new professor whose expertise would be in life cycle analysis. So some of us in our courses, we have a certain segment about life cycle analysis, but it's not a dedicated course. And so we cover in a lecture. So the importance of it, and give students an understanding the difference between cradle to gate and cradle to grave and cradle to cradle. They get to understand what hotspots identifications are, problem shifting, but certainly we would have enormous benefit if we could have that, if we could make that higher. A little tough right now with COVID going on, but nonetheless, I think that's terrific that you're taking a course with that over in Northeast, a dedicated course.
If I could just jump in one quick second, there is a life cycle assessment pamphlet out there on the internet of the Olver design building. It was done on a full environmental building declaration. So the entire building was assessed. So, and compared to a theoretical building of the same size made out of a steel structure. So it's being done more and more, comparing entire buildings, and you can find it if you're interested. Just Google EBD, or actually the Olver design building, is it Innovation to Implementation, Alex? I can't remember the name of the flyer.
So you know what? If you send me an email, I'll send you the link. I'll send you the full document. There
Anyone
you
who's
go.
interested, ask Carl.
There's service.
There you go.
All right. I think we are just slightly over time. So I'd really like to, in closing, thank Ms. Jandris for a great presentation and a good discussion at the end. And I'd like to alert her to the arrival in her mail of the much coveted BCT water bottle.
Well, thank you.
So you stay alert for that. It's a small token of our thanks for you coming and doing this. And there'll be a PDF coming of students' responses to this presentation, which is interesting. So thank you very much. And before we go, I'd like to alert you to the 4th and final BCT lecture on November 2nd. It's a better way to build in the 21st century, with Mr. Ted Benson, who is the founder and CEO of Bensonwood, which has had national impact on from early timber framing on to factory production of individual elements, and now onto whole houses. So that will be on November 2. And thank you very much. And if we could have some virtual thank you and applause for Ms. Jandris. Thanks very much.